Greetings. We are the FPGA Accelerated Obstructed Face Identification Team. Let's meet the team.
Hello, my name is Ignacio Acevedo.
Hello, my name is Gabriel Colon.
Hello, my name is Kevin Horta, and this is Michael Vasquez. As we all know, the number of cases of COVID are rising each day. One of the main reasons is because of the misuse or lack of face masks. We want to help control this factor that helps spread the virus. Our main goal is to develop an FPGA-based system that can identify if a person is correctly wearing a face mask that is incorrectly worn or is not wearing one. This project was proposed by Raytheon to the university and Dr. Raúl Torres offered as a project for the capstone course. Our main objectives are to develop an algorithm and implement it on the Ultra 96 V2 board using images from a database. We want to design and print a case for the board by using a CAD program and a 3D printer. And lastly, design an indicator that can show the results to the user.
Here we have the hardware connection schematic versus the actual connection. As you can see, the JTAG UART has no connection on the actual connection because it was used for the initial setup. After that, you just connect the host PC to the micro USB to access the Jupyter notebook.
Using the Pink 2.6 framework, we followed two options. Option 1. Implement code utilizing OpenCV's hard cascade models for feature recognition. Option 2. Implement a trained neural network to determine the user's mask wearing status via image processing. Here are some examples of the images used for the algorithm. Exploring option 1, Python code was implemented on the Ultra 96 V2 via Jupyter Notebooks. It utilizes OpenCV's hard cascade detectors for facial feature recognition. It recognizes faces, eyes, nose, mouth. By detection of these features, it determines if a person is wearing a mask or not. It can utilize images from a dataset or capture images from the webcam. The accuracy was around 91.14% correct readings out of 139 selected images. Here we have a flowchart with if-else conditions that check if faces, eyes, mouth, and noses were detected and output a corresponding detection. Here we have output images of the algorithm. In the upper left, we have the no mask images that identified face, eyes, nose, and mouth. In the upper right corner, we have incorrectly worn images that did not identify the mouth, but did identify nose and eyes and face. In the bottom, we have the correctly worn images that identified eyes, face, but no nose or mouth.
As you can see, this is the result of running the code for the camera detection code. First, it took a picture of me wearing correctly a mask. It detected my face and eyes, resulting that it classified that I'm correctly wearing a face mask. Then, it took a picture of me for incorrectly wearing one. It detected my eyes and nose and face, but didn't detect the mouth. It classified that I'm incorrectly wearing a face mask. Lastly, it took a picture of me not using a face mask. It detected my eyes, my nose, and mouth and face, resulting that I'm not wearing a face mask.
For the object detection neural network, we used the YOLO before Tiny Object Detection Network, which was trained with over 900 images from the dataset. Its best mean average precision was 92.8% accuracy, and it has two modes of operation, which is detection from dataset and detection from webcam snapshot. Here we have the detection images from the dataset. As we can see on the top left corner, we have the correctly worn mask with the bounding box on the region of interest. On the top right corner, we have the incorrectly worn mask, again, region of interest with the bounding box to display the mask. And on the bottom part, we have no mask worn. As we can see, the region of interest is within the bounding box. Here we have the detection from webcam photos taken of myself. On the top left corner, we have the correctly worn face mask. As you can see, the face mask is surrounded by the bounding box, the region of interest. On the top right corner, we have an incorrectly worn face mask, and on the bottom, we have no face mask worn.
Here I'm going to explain the Vivado Design Suite. Vivado Design Suite is composed of Vivado HLS and BT's HLS. It is also compatible with the Ultra 96 V2. In order for the algorithm to be implemented into the FPGA, it has to pass through the IP integrator, the C simulation, synthesis, implementation, and bitstream. In the IP integrator allows the user to configure hardware settings. In the synthesis process, the VHDL design is converted into a logic component, and the bitstream is a file that contains all of the programming information. As an alternative approach, a block diagram was created, implemented, and synthesized to control one output port of the Ultra 96 V2. Then, the bitstream file was generated to export it to ByteDance HLS program that is compatible with the C language. Then we added a source code based on the Viola-Jones algorithm into the ByteDance HLS, and we amended as the C code so that when a person without a mask is detected, it turns on one of the output ports for a period of time. Finally, the code was downloaded into the Ultra 96 V2 micro SD card.
This is the case that was designed for the FPGA. This is how it looks after printed. This is a 360 view of the case. The dimensions are approximately 193 and 26 millimeters.
Thank you for your time and attention. If you have any questions, please feel free to contact us at our indicated emails at the beginning of the presentation. Thank you.